So I think this is a good moment to pause for a second and ask, what is it that we're doing? In order to answer that question, let me just give you an analogy. Okay. That comes from particle physics. Okay. We all learn quantum field theory in order to describe particle physics. Imagine that we're doing, say, quantum electrodynamics. Okay? What do we have there? We have a gauge boson and, say, some field that describes electrons. Okay? So we want to write a theory or construct a theory for electrons and photons. So we have quantum field theory, and what we do is to construct fields. Okay? So these are now fields. And we write an action for these fields, and we quantize them. And now these fields, just as an example, the field coming from quantizing the photon will produce something that has some creation operators with some polarization vector and e to the I t dot x plus other terms. Okay? And then what happens is that if you take one of these operators and add on the vacuum of the theory, you produce a quantum of the photon field. Okay, so this will be our photon. Now you could also quantize this guy. And remember there, we have some creation operators to these. And you can act with them on the vacuum to produce quanta of electrons. So you produce your photon and you produce your electrons by acting on the vacuum of your theory. Okay? So that's what we do in quantum field theory. Now, but suppose that people didn't know about quantum field theory. What else could they do? Well, if you didn't have quantum field theory, you could try something that we could call the world-line formalism. And in this approach, what would you do? In this approach, you would describe particles by mapping, by thinking about them as a 1,0 or a 1 plus 0 quantum mechanics. Okay. So you could have one for the photon and one for the electron. Okay. And we will map this into some space-time where you will have the photon and you will have the electron in the space-time. You quantize this theory here, it will have its own vacuum, and you will produce states. And these states will be vectors in space-time. Okay? But now what we're producing here are the wave functions. So these A's will be the wave functions. In space-time. Likewise, these guys will act on their own vacuum, and they will produce these wave functions. So these are now wave functions. So they look like different theories, but now we can impose rules on how these things can actually interact. So we will construct diagrams by hand that will put these guys together and produce another one It's like doing plumbing. You just put different tubes, connect them, put the next one, and so on. And ask, well, can we build a consistent theory of interactions playing that game, of connecting these different guys and put them together to produce another one, and so on, and produce a consistent theory of interactions? Okay? Well, we know the answer is yes. It might be painful, but the answer is yes. But the reason we know the answer is yes is because we now know how to do a much better version of that. We have a quantum field theory that does all that for us. We don't have to do it by hand. We don't have to put interactions by hand. Okay? So what's the difference between these guys and these guys here? What is this A here and what is this A here?
The first an operator, and the second derivative is just a function.
Excellent. This is just a function in space-time, and this is an operator. Okay? Very good. So in a sense, we have the luxury of doing quantum field theory in space-time, which is the best formulation of a relativistic theory of quantum mechanics that incorporates special relativity and quantum mechanics. But if our friends from the past 70 years had not been that smart, we would be suffering with this formulation. Okay? So thanks to them, we have a very elegant and nice way of talking about fields. Okay? So how about in string theory? Where do you think we are? Yeah, we are here. Right. So we have a wall sheet theory, right? We're mapping into space-time. So we have some vacuum here, and we have some operators. Just one that we had yesterday. And we produce, again, a wave function, okay, for some gauge potential in space-time. Say this was in the NS sector, right? Now, we can also have the Ramon sector that ends up producing a wave function for a fermion in space-time. Okay? Now, of course, wouldn't it be nice if we had the analog of this? So how would you call that? Of course, people have thought about that. And they call it string field theory. Yes.
Maybe it's I just was wondering if in the Ramon sector we have only fermions and in the usual sector we have only bosons.
Yes. Well, in space-time, they produce the wave functions of only fermions or the wave functions of only bosons.
Okay.
Right? Remember, from the wall sheet point of view, the wall sheet theory has X's and psi's, right? It has both. In fact, it's supersymmetric. So wouldn't it be nice if we had a string field theory? Well, of course, this is just one of the guys that this thing produces. We can have tons of them and alphas. Okay? So this is really an infinite tower of objects that this single theory is producing. Likewise, here we have an infinite tower of these and alphas acting on the vacuum. So we have an infinite tower here. Okay? So wouldn't it be nice if we had a string field theory? Of course it would be nice. So what would be the string field? So we can call it, say, something like this. And what would this guy do? Well, this would be something. Now here, the fields depend on a point in space-time. So this guy would actually be a functional of paths. Okay? And the job of this guy, if we were to expand it, the creation operators would create what? A whole string in one shot. So the quanta of this thing would be actual strings. Okay? Well, there's been progress, lots of progress on having an open string field theory. Started by Witten. And there is some progress in closed string field theory. But in this course, we're not going to talk anything about, this is all I'm going to say about string field theory, okay? It's just so that we know what is it that we're doing, okay? And why we're not doing what you usually do in quantum field theory. And the reason is that we still don't have a good handle, or we still don't understand completely, sufficiently well what this thing is so that it can be taught in a course, or at least in an introductory course, okay? So this is an open, this whole area is a big area, and anyone who wants to jump in is welcome to jump in and try to push it so that maybe in 20 years, somebody would be saying, well, thanks to these guys who are very smart, we're not doing this. We're actually doing string field theory. Okay? Okay. Well, just like in this case, we could call these different sectors. These are different sectors of the theory. Okay? But sectors of the same theory. How do we know it's the same theory? Well, because we can find rules on how to put them together and make them interact, just like we can do it for the electrons and the photons here. Okay? So what is a theory? Well, we don't know how to write the string field theory, but if we just concentrate on the massless sector, okay, just the first level of the whole towers of states, we can write down a field theory that will describe the interactions of these particles. And that's what we call the low energy effective theory. Okay? This is a field theory. So you see, whatever the string field theory is something that contains an infinite number of field theories in it, right? Because we are going to get a field theory just from the first level, just from the massless guys. We're going to write a full field theory. Okay? Well, what is it? Well, the fields are a gauge potential and a Majorana Weyl fermion in 10 dimensions. And the effective action turns out to be I want to get all the factors right because you might want to go ahead and check that this 10-dimensional action, know that this is our first 10-dimensional action, right, is invariant under these transformations. Where epsilon is also Majorana Weyl spin. Okay? This transformation should be very similar to the one that you did on the wall sheet. And this is supersymmetry in 10 dimensions. Now, epsilon being a Majorana-Weil spinor in 10 dimensions means that it has how many real components?
Physical first?
Sorry? Oh.
Maybe down.
From the left corner.
Yes. Can you put it down?
And you can forcefully push it down. And then bring it.
Brilliant. Okay. Well, let's not stop the progress of science just because the blackboard doesn't work. Got tons of blackboards all over the place. Okay. Well, you had time to think about how many components we have. So, (16 real components). Okay.
But we are considering the transformation on shell, right? This percentage transformations are on shell.
Yes, indeed. This is invariant at a total derivative, right? So that's what you should find. If you try the exercise, you will find that this is invariant under these transformations only up to a total derivative, okay? After using the equations of motion, or the field equations, yes. So this guy has 16 real components, okay? And people call this theory, given that you have just a single spinor parameter for the transformation, so only one spinor, people call this n equals 1 SUSY in 10 dimensions. Okay? But it's also convenient to talk about the number of real components in your transformations. Okay? So people also like to talk about this as a theory that has 16 supercharges. Okay? So each component, we think about them, or we call them, a supercharge. So this theory has 16 supercharges. Do you know any other theory that has 16 supercharges? N equals 4 superyammials. Remember that we started the lectures talking about supergravity and superyammials in 4 dimensions. So we said in 4 dimensions, we could start with a state with -1 helicity, and we said that, well, supersymmetric transformations act like a fermionic operator that raises the helicity by a half every time it acts on a state. So we did this on this state with -1 helicity, and produced one with helicity -1/2. And then we're done, because if we only have one supercharge, if we only have one operator, then the next one will give us 0, because these guys are nilpotent, right? So the q squared will give us 0. But if we had many of them, in particular we had 4 of them, so we can put an index here and an index here, and we can keep going. How many guys we get here of helicity 0? Four of these guys. We just get one state. So how many of these guys we get? We get 6 scalars, right? Because this is antisymmetric. Here we only get 4 states. Here we get 4 states. We get 1 state and 1 state here. Of course, we know that as a field theory, we can describe these 2 guys as a single. This one and that one will produce a single gauge boson, or will be described as a single gauge boson. This one and these ones will be described by 4 spinors And these guys will be described by 6 scalars. So we can put another index. Let me call it, let's call them explicitly 5.1, 5.2, up to 5.6. So we have 6 scalars, 1 gauge boson, and 4 fermions. Okay? Now, could there be any connection between that and this 10-dimensional action? Well, remember, after all, we want to go to 4 dimensions, and we have 10 dimensions here. So if we want to produce a theory in 4 dimensions, the simplest thing to do is to compactify all the directions that we don't want on a circle. So why don't we try to compactify this or reduce to a Kaluza-Klein reduction on a torus of 6 dimensions, which is nothing but 6 circles. So we take 6 of the 10 dimensions, and we think about them, each one of them as a little circle of a small radius, and we do a Kaluza-Klein reductions of these fields. Okay? And what happens is that, say, our 10-dimensional gauge boson, this is our 10-dimensional object. So let's write the components explicitly. Say we have the components 1, 0, 1, 2, 3. So we have all those components. And let's pretend that we're compactifying on circles these guys. Okay? Now, from the point of view of the 4-dimensional Lorentz group, right? So we only care about 4-dimensional Lorentz invariants because we are breaking Lorentz invariants in 10 dimensions by going down, by compactifying on a circle. We don't have Lorentz invariants in the full space anymore. We only have Lorentz invariants on the 4 directions that we are not compactifying. So our 10-dimensional space, so what we're thinking there is that we have our 10-dimensional space, and we're running it as R1 plus 3 times this T6 torus, okay? So these 4 guys here, how do they transform under the 4-dimensional Lorentz group? What are they? They are a vector. So from the 4-dimensional point of view, these guys are a vector. From the 4-dimensional point of view, what are these guys? Scalars, because you do any Lorentz transformation in these directions, and even in 10 dimensions, these guys will not even care what's going on by applying a Lorentz transformation only on these directions. So these guys don't see any action here, and therefore these guys are scalars. And who they are precisely these 6 guys. Okay? So our first quantum field theory that we get in 4 dimensions that comes from string theory can be said to be n equals 4 super Young-Mills. Okay? Of course, it's not quite super Young-Mills, right? Because what's the gauge group? Here. How many gauge bosons we have? How many? 1. So what's the spectacular gauge group that we have? U1. Okay. I mean, that's a start, right? So we got a U1 gauge theory, and we got a U1 gauge theory in 4 dimensions. So it's n equals 4 super Young-Mills. Or we could call it n equals 4 super Maxwell. Okay. So we got n equals 1 super Maxwell in 10 dimensions goes down to n equals 4 super Maxwell in 4 dimensions. Okay? All right. But you didn't come here just to see super Maxwell, right? The idea we're all here is to see gravity. And in order to do that, we have to consider closed strings. And it's really unfortunate that maybe we should try Have you seen this problem before?
No.
No? Okay. That means that,
Yeah, a little false always helps.
sorry?
A little forceful behavior always helps.
You wanna try?
Oh.
You want to say?
That's what you say, right?
Okay.
What the? No, nobody's moving. Okay. I think this is dead. All right. Well, we haven't been stopped by ghosts, vacuums. Are we going to stop for a problem? No. Okay. As long as this one works. Okay. Okay.
Freddy,
Yes.
why did you say we had V1?
Oh, because we only have one gauge boson, right? And this action is invariant under let's call it phi, say, right? And the corresponding transformation on the fermion for it to be an electron, if you wish. That's a U1 transformation, right? For the infinitesimal version of a U1 transformation. Yes.
So is the electron really coupled to a mu in this action?
Yeah, sorry, yeah. I should have. It was a capital D. Okay. So if we want to do closed superstrings, now the bosonic sector is the same as before, so there is nothing interesting to try there. The closed string boundary conditions are the same as before, the oscillators, everything. So we're not going to worry about that. So we have to look at the fermionic sector and ask, what are the boundary conditions that we can have for the closed string? So we are just going to look at the boundary conditions. This is a formula that you should have on your notebooks from last time. This is a result of the variation now from the boundary terms at sigma equals to pi. And at sigma equals to 0. Sorry, in fact, in this case, we want to think about these fields as being in the adjoint representation. So in this case, this guy is actually, yes, a derivative. So they don't really talk to each other. We'll have to make it non-abelian. Okay? All right. So in the open string, what we did was to set this equal to 0, so we have to set this equal to 0. And we did it, so it would be nice if we had, well, we can do it like this. In the open string, we cancel these two guys and these two guys. So the notation is that this means open string. Okay? Now in the closed string, what we want to do is to cancel this term, and this term, and this guy, and this guy. So this is the cancellation for the closed string. Okay? So in order to do that, what possibilities we have? Well, the possibilities are we can choose psi plus for all the components to be related to psi plus when the sigma component is shifted by pi. We can choose it to be plus or minus. Any of the two choices will satisfy the boundary conditions or will make this equal to 0. And we can have the same thing for psi minus. Okay? So when we choose the choice of periodic boundary conditions is called Ramon. So if you choose periodic boundary conditions, you're saying that you're working in the Ramon sector. And if you choose anti-periodic, you say you're working in the NS sector. Okay? Let's just say R. Okay? So in this case, how many sectors we have available? We have 4 sectors, because we can make choices for these guys and these guys independently. So we have 4 possible choices, and therefore 4 possible sectors. Now, with the choice of sectors also comes the question, how many different theories we can have? How many of these sectors can we put together in such a way that they interact in a consistent way? Okay? So it turns out that there are 2 possibilities of combining sectors. So there are 2 possible theories, and the theories are characterized basically by what you do to the Ramon vacuum state in each of the sectors. Okay? So let's see how that works. So we are saying, all in all, we have 4 sectors. We can combine from the left movers and the right movers. We can choose Ramon boundary conditions for the left movers. So let's actually write it here. So we now have left movers and right movers. Okay? And we can choose boundary conditions of the form Ramon-Ramon, Ramon-Navier-Schwarz, Navier-Schwarz-Ramon, or Navier-Schwarz, Navier-Schwarz. Okay? So these are the possibilities. Now, what theories can you produce? So the theories are classified by the choice of the Ramon vacuum state in each of the sectors. Remember, the Ramon vacuum state is a spinor. It's a massless spinor, so it can be, it's a Majorana and it can be vile, right? Remember that the GSO projection told us that we have to choose one of the two chiralities. So we have two choices. For the Ramon vacuum state, we can choose this guy to have positive chirality, okay? And we choose, so these are the left movers. And these are the right movers. So recall that we had the convention of calling left mover oscillators to put them a tilde on top, just to remember that they are left movers. And the right movers were the oscillators without the tilde. So we can have this choice. And on the right sector, we could also choose to just stick to the plus helicity, to the plus chirality Ramon sector. And for the Navier-Schwarz sector, well, we don't have any choices. We just have the vacuum state, the usual vacuum state. Okay? So this turns out to give us one consistent theory. Okay? The combination of the four sectors for this choice of vacuum of the Ramon state in the left movers and this choice of vacuum in the right movers give us one consistent theory. We could also choose to have another theory which would be constructed out of these guys. Okay, so on the left movers, we choose just the negative chirality Ramon sector, or Ramon vacuum, and on the right, we choose the plus chirality. Okay. Now you would say, how about the plus minus and the minus minus? Well, those theories are all equivalent, okay, to either this one or this one. So these are the only two inequivalent theories that we can make. And what we're going to do now is to study each one of them in detail. Yes?
You said that these two are consistent, but what do you mean by consistent? In the interactions, in the whole part of interaction?
Yes. So, well, first of all, the GSO projection tells us that we can choose only one and not both, right? So, really, these are the only choices we even have. Yeah, I didn't even have to say consistent, right? Because we cannot choose both Ramon sectors here. So these are all the choices we have, and they turn out to be consistent, meaning that you can combine these sectors into a single theory that makes sense, okay, where the interactions are consistent with the choice of sectors that you made. Okay.
So you mean like if we start by two states from the up sector, we will end up with two states in the same sector?
Now remember, I'm trying to make a distinction between sectors and theories.
Okay, who's from the up theory?
Each theory will have four sectors, right? So this theory will have four sectors, and this other theory will have four sectors.
I meant like if we start with the state.
If you start with this
sector.
choice, this theory by itself with its four sectors will be a consistent theory by itself, okay? And this will be another theory with four sectors. Now our job is to understand what these theories are. So let's start with the first one, okay? So theory one. So what do we mean by the Ramon-Ramon sector? Well, we mean the states that we can create by taking as vacuum state the Ramon vacuum state here and the Ramon vacuum state here. and apply oscillators to them. Now we're only going to write here explicitly the massless sector, massless states, which conveniently, remember we got rid of the tachyon, so the massless states are the vacua of each of the sectors, right? In the Navier-Short sector, the GSO projection killed the tachyon, and now our new vacuum in the NSS sector is precisely this guy that I wrote here, which happens to be massless, right? So this would be the Ramon-Ramon massless states would be produced by taking this tensor product. The NSR would be, well, what you would expect, B tilde I minus a half NS cross plus, okay, Ramon NS would be plus R cross B minus half. And finally, we will have okay. Now, these are massless states, so they must fall in representations of SO8, which is the little group of the Poincaré group in 10 dimensions. Okay? Well, out of all these guys, I think the only one that I can ask you right away what answer we give is this one. So what kind of fields would this produce in space-time? So we have two vectors of SO8, and we have the tensor product of these two guys. And we want to write it in terms of irreducible representations. We know that if we take the tensor product of two vector representations, that's not irreducible. There are pieces inside it that will transform, that will not mix with the others under any SO rotation. That means that there are irreducible representations sitting inside this representation. Sorry?
How do we know that?
You should definitely do. You did it in a tutorial, probably a homework, and we did it for the closed string. The only difference in the closed string is that these guys were taking values from 1 to 24, right? So how many states we have here? We have 8 times 8. So let me put the V to remind myself that these guys are vectors. So we have 64 states, right? And they split in irreducible representations. How do they split? Well, the antisymmetric part, the antisymmetric combination, right, of these guys cannot mix with anybody else. So that will give us a 28-dimensional representation, right? What else we have? Yeah, finally our graviton, right? We need our graviton, which is the symmetric traceless part. And we have the trace, as somebody here said, and that should add up to 64. Okay? So our friend here in space-time will be described by a field that we call G mu nu. This one in space-time in 10 dimensions will be described by a field that we call B mu nu, and this one by something that we call phi. Okay? So what do we do with all these guys? Well, that looks a little bit complicated. So let's try a toy model. Yes.
Do we need to have all the sectors?
Yes. Yeah, we need all 4 sectors for this theory to be consistent. Okay. So let's try out a toy model that I hope you will be more familiar with than SO8. Okay. So what's our toy model? Well, let's consider SO6. Do you remember what the thinking diagram of SO6 looks like? What's the rank? 3. Right? Well, the thinking diagram of SO6 looks like this. You remember? Well, it's a funny way of writing. Remember, the thinking diagram of SO groups is something that looks like this. In general. But if we only have rank 3, well, it turns out looking like this. Well, but that thinking diagram looks like the thinking diagram of something else. What would that be? SU4. Not quite, because this one is actually like this. Now you see that it's exactly the same. Now what's interesting is that, I don't quite remember if we said it, but yeah, I think we said it, that the representations are classified by the highest weight. And to each node, we can associate a particular representation, which are called the fundamental weight representations of the corresponding algebra. Now, in general, in SO, these 2 guys are associated to the spinor representations. Okay. Well, in this case, this will be our spinor representations. But that's funny because they look like these representations here. And the first guy here that we have is the fundamental representation that we write as a box. In SUN, we write it as a box. What's the dimension of the fundamental representation in SU4? It's a fundamental representation, so it must be 4, right? The dimension is 4. What's the dimension of a spinor with positive chirality in SO6? Well, in general, it will be 2d½ minus 1, right? The dimension of these guys. Well, if we put 6 there, we happen to get 4. So that kind is actually matching, right? And this guy turns out to correspond to the anti-fundamental representation of SU4, which also has dimension 4. Okay? Now, why am I doing this? Well, because here, you see what we have to do. We are now taking the case we want to consider is actually SO8. And the thinking diagram looks like this. And the dimension of the spinor representation here is 8. Here is 8. Okay? This one has 1 chirality. Let's call it plus, and this one has a different chirality, so let's call it minus. But you see that this thinking diagram has a very interesting feature. It's symmetric under rotations by
120 degrees.
Sorry?
120.
Sorry? You said what?
No, 120 degrees.
Yes, that's true. Thank you. Yes. It's symmetric under rotations by 120 degrees. So it means that this representation, if you just rotate this, the representation associated to this node should have the same dimension. But do you know any other representation of SO8 that has 8 dimensions?
Sorry.
The vector representation. Just a single vector will have 8 dimensions. Okay? So in order to decompose this state here, we have to know what the tensor the composition is of two spinors of the same chirality. Okay. Well, but we know how to do that here, right? Say two guys of the same chirality would correspond to taking two of these guys together. Right? So this would be, we can call this again plus and minus if you wish. From the point of view of SO8, they would have different chiralities. So this would correspond from the point of view of SO6, sorry, from the point of view of SO6 to this tensor product. Well, but you're all experts in Dinkin diagrams. I'm sorry, in John tableau, right? And we know very well how to compute, how to decompose this in irreducible representations. We just do this and this, right? And we are all experts in computing the dimensions of these guys. So this, the dimension of this is 4 times 4 is 16. And what is the dimension of this guy? Well, the dimension of this guy would be, we have to do this little computation. This is, we get here 4, we put here 3, and then we put here 2, and we put here 1, and we get 6. The computation of this guy if you don't remember what I'm doing, you should go back to what we did at the beginning of the course. So here we have 4, 5, and here we have 2 and 1, and that gives us 10. Okay? Very good. Now, these are the representation in SU4, but we want to ask, from the point of view of SO6, what could they be? Any guesses? SO6 basically has this vector index all over the place. Is there anything with vector indices we can make which will have dimension 10 and 6? Sorry?
6 could be vector.
Could be a vector. Yeah. Very good. So this will be a vector, right? How about this 10? Oh, that one is very tricky.
Assumption and symmetric. And symmetric matrix.
Yeah, well, let's count. How many components does it have?
Oh, no, it's not.
Has it be self-dual?
Well, yes. So there will be something. Yeah. So, but self-dual what? In 6 dimensions, what can be self-dual? A 3 form. Well, let's count a 3 form. How many components does a 3 form have in 6 dimensions? Well, it has 6 times 5 times 4 divided by 3 times 2 times 1. And this is equal to 20. But in 6 dimensions, we can impose a further condition. And that condition is preserved by SO6. So if we can split this guy into objects that satisfy that condition, then it means that those guys are irreducible representations. And the condition is that the Hoche dual of the form happens to be the same thing, or the Hoche dual of the form happens to be minus itself. Okay? So people like to call this something that satisfies this A plus, and something that satisfies this as A minus. So our 3 form is not an irreducible representation. It decomposes as A plus, a 3 form, plus an A minus 3 form. But since they are isomorphic, they split into 10 plus 10. So this representation splits as 10 plus 10. Okay? So one of them will enter here, say A plus. So we decompose the tensor product of these 2 spinors, and it gave us these 2 forms. Okay? So I encourage you to play with all possibilities here. Try to take tensor products of everything that you can do here, and give an interpretation as representations of SO6. As SU4, you should do it. You should be able to do it in a split of a second, because you know all these techniques. Now the catch will be to go back and say, well, what happens with these representations? What are they from the point of view of SO6? Okay, and once you do that, see the time. So once you do that, try to convince yourselves that the following is true for SO8. So if you have the tensor product of two negative chirality spinors, that will produce, that is 64, right? So that's going to be interesting, because it's exactly the same dimension as what we had there. And in fact, remember from this triality diagram, I mean, the symmetry is called triality, because we can swap this. This is the tensor product of two guys in the same representation. So if I have two spinors of the same chirality, the decomposition has to be exactly the same as the one for two vectors, right? At least in terms of dimensions. But wouldn't this be a disaster? If that 35 happened to be the same 35 that appears there, we would be in trouble, because we will have two gravitons.
Where do you go 8 minus cos 8 minus?
Yes. So I'm calling this representation A minus, which in this language is, well, sorry. This one is A plus, which in this language is this guy. This one is 8 minus, which in this language is R minus, where, of course, minus doesn't appear in this theory, but it will appear in the other theory. And this guy is A vector, which is our BI minus Navier-Schwarz. Okay, that's the translation. So we are computing this tensor product. Of course, I know why you're complaining. You're saying, why worry about these guys if they don't appear in that theory? Well, but hey, don't be so picky. These guys are two positive chiralities, so they should also have the same thing. Now you should worry, right? If this guy decomposes like this, and this 35 happens to be a graviton, we will be in trouble. We will have two gravitons in the theory. And that is known to be inconsistent. Well, this guy, once again, is an antisymmetric tensor. Okay? That's what it is. But this guy is not a graviton. There is another representation that has dimension 35 for SO8. What could that be? Get any inspirations from the 10 example over there? For SU4, we had this 10-dimensional representation.
5, 5.
It's a self-dual 4-4. So it's something that has indices I, J, K, L, right? It's antisymmetric, so if you compute the dimension of this guy, you get 70, okay? But it decomposes as 35 plus 35 minus in terms of self-dual and anti-self-dual. And in this case, well, you can guess. In one case, you get a minus, and in the other case, you get a plus. Okay. We already did, well, let's do it here. And the vector is 1 plus 28 plus 35, where the only difference is that this guy happens to be our traceless symmetric tensor. The new guys are these ones. Say, this is equal to 8 vector plus 56. We can also call it V. And this guy is a 3-form. Sorry. Let's put the indices ijk here.
Question.
Yes.
Now we are working in SO8, but in the real string theory, the thing that has to be self-dual is the field strength, not the 4-form, right?
Yeah, but that condition comes from, So these are the on-shell states. So they have to fall into representations of the little group. Now the question is how to describe them in a nice local way in a Lagrangian. And the answer is that this guy will be represented by a gauge potential, right? A 4-form gauge potential whose field strength will be self-dual, right? In 10 dimensions, a 4-form cannot be self-dual, right? But that translates into the same condition. Yes. Very good. So we have this. And we are still missing, what else are we missing? So we have to write down all possibilities. Are we missing something? So we have that.
Question?
Oh, we can have, yes?
Question? Is the small geminio the same as the big geminio?
Yes. So actually, let me write this ij. Just because we're doing the counting here, okay, of the dimensions by counting the little group indices. So this is the vector with the plus chirality spinor. Well, you see, once again, if these guys are different, we should get always the same thing, at least in terms of the counting should go, because the algebra has the triality. Okay, so in this case, we get something that looks like this, plus this guy, and we get something that looks like this, cross A minus, it will be okay. Now, after all that, we can spend 5 minutes using all that technology to read out what the spectrum of this theory is. So we can start from here. This is the plus plus. So we go to the table and look, and we say, well, it has a 1 plus 28 plus 35. This guy. So we have another scalar in the theory. Let's call it phi. We have another 2-form. Let's call it B mu nu RR, because it comes from the Ramon-Ramon sector. And we have our friend here, which is our self-dual 4-form. I think, what do I want to call it? D.
Is that the dilaton?
Yes?
Why do we call it D? Because we had D before, which was the dilaton.
No, the dilaton was phi, but they're different phi.
Right.
Yeah, the dilaton was phi. Yeah, this is the dilaton. Okay, we have the dilaton, the B field, the graviton. We have this guy, which we can call the axion, if you wish. We have a 2-form that we will call the RR 2-form, and we have this 4-form, which we'll just call a 4-form. There's no name for that. Okay. How about this guy? We go to the table. We go to the table, and this is A vector with A plus. Just look at A vector with A plus, and we get and the same thing here. We get exactly the same. Now, what are these representations in space-time? What kind of fields? Well, this will give us spinors in space-time, massless spinors, right? So we get 2 spinors, and these are called dilatinos. I'm putting an I because we have 2 of them, and they are identical. They have the same chirality, right? The chirality is inherited from the chirality of the Ramon ground state. And we have something that is 56-dimensional, or at least has 56-dimensional degrees of freedom, or only 56 physical degrees of freedom. And that object turns out to be a gravitino. And we also have two of those. Okay? So this is our first theory. Now let's do here theory 2. So what was theory 2? It was a theory where we chose different chiralities for the Ramon vacuum states. So in the Ramon-Ramon sector, we have something like this, right? Which, if we look at our table, will give us an A vector plus 56 vector. And this guy will be a 1 form. And this guy will be a 3 form. NS our sector, we get sorry, this means plus. Now it becomes more interesting, right? Because these two guys, in terms of the dimension of the representations, are the same, but the chiralities are different. So we get, once again, 2D Latinos, or 2D Latini, if you wish, 2D Latini, and they have different chiralities, while there we had the same chirality. And here we have 2 Gravitini, again with different chiralities. And last but not least, we have the NS sector, but that's exactly the same. The two theories have the same NS sector, which is B tilde minus a half Okay? So people gave names to these theories, and the names are not very illuminating. They are meant to represent something. And what the names are meant to represent, first of all, is the amount of supersymmetry in 10 dimensions. So the name we're going to give to this theory has to do with the amount of supersymmetry. How much supersymmetry you have? Well, you can already tell by the number of gravitini you have in the theory. You have 2 gravitini. If we had only 1 supersymmetry, you would only have 1 superpartner for the graviton. But here we have 2 gravitini, so we have 2 supersymmetries. How about here? Well, we also have 2. So the 2 will not tell us how to differentiate the theories. But nevertheless, people call these 2 here and 2 here. Okay? And for some reason, which I don't quite know why, the one that has both chiralities is called the A theory, and the one that has the same chirality is the B theory. So this is a chiral supergravity theory. Why is it chiral? Well, it's chiral because if you apply a parity transformation that reverses chirality, the theory doesn't stay the same. So this theory is actually chiral. But in this case, the chirality will flip these guys, and this theory is non-chiral. Okay? So those are our first two 10-dimensional superstring theories, which are tachyon-free, and they are all consistent by themselves. Of course, you can start asking, what does the interaction of these guys look like? What is the low-energy effective action of these guys? But you already did that last week. With Lilia, you wrote down the low-energy effective action for all these fields. Okay, so look in your notes, and you will find the low-energy effective action, at least for the bosonic fields. I'm not sure if you did the fermionic fields. Okay? And you probably realized with Lilia, too, that this theory, even though it looks complicated in 10 dimensions, at least the supergravity part was a Kaluza-Klein reduction of a theory in 11 dimensions. So that's very interesting. How about this theory? Could this theory be? Well, this is the low energy effective theory of this guy that comes from studying the low energy effective action of these fields. Is the one that you're doing in the homework this week. Okay? Now, do you think that this theory can come from the Kaluza-Klein reduction of something? You think?
From a theory?
Well, not really. Because those two dimensions are not really dynamic. Well, one simple way to say, well, I doubt that it's going to come from something like that is the following. This theory is chiral, right? So if it came from an 11-dimensional theory, say, right, in 11 dimensions we don't have chirality. So when you compactify, how do you choose one or the other? That's the reason when you go down, you get the two different chiralities for type 2A, because you started out in a theory that didn't have chirality. Okay? So that might give a little bit of a puzzle, right? We know the standard model has chiral matter, right? So I'll stop with just this puzzle for you. So try to think about that. In 4 dimensions, we know the standard model is not a non-chiral theory. Or we know that the standard model is a chiral theory in 4 dimensions. So how on earth can we get a chiral theory by doing a Kaluza-Klein compactification of anything? Even here, you would say, well, start with a chiral theory. But the moment you compactify on a circle, you go down to a theory that lives in 9 dimensions. And there is no chirality in 9 dimensions. So when you keep down, you already lost the chirality. If you keep down compactifying on circles, you lost the chirality. So that's just to give you another example of another problem that people thought was going to be impossible to solve. And in the end, ended up being solved in a very interesting way. So as usual, these puzzles give you usually new ways of thinking. And finding the resolution to the puzzle is usually a way to make important discoveries. So we will stop here and continue tomorrow with a way of connecting these two theories, in fact. But in order to connect them, we will have to go to a space where they have the same structure. That's a hint for what we're going to do.